we kind of will present basically in two parts. I will start and Errol will end up our presentation. Just to make sure everything is clear, I'm presenting as a resource expert, not as an RC person. Just we are presenting our model. Okay, our model was, yes, I have, okay, I don't know, I don't have these questions, but anyway, our model is different and it's developed outside of NGA project, and this is why I will spend a couple of minutes to explain the model. The difference, basically main difference, is that our PGA model is structured as a bunch of filters. And each filter represents certain physical phenomena. For example, number one is magnitude scaling, core attenuation is another function, anelastic attenuation, side correction, and basin effect. That's what we have now in our PGA model. And again, the difference is, as you can see, that PGA is a multiplication of filters. In log space, it is a summation. This model was first developed in 2007, published in 2007, and extended to SA in 2009. After that, recently we updated this model. This is why it's called updated Greiser-Kalkan model, or GK13. Now, speaking about spectral acceleration is a function. That's another difference from standard models. We approximate SA as a function, spectral shape as a function, and its smooth function right now it's tested up to 10 seconds, but basically in principle you can extend it to longer periods. Of course, it's not constrained at longer periods. And it's structured in a way that it's anchored to PGA. That's kind of basics of the model. Now I will go to the questions. I'm sorry, I will answer these questions probably in different order, but anyway, I try to work on this. Okay, main question that we have is that our model has a bump, at least for magnitude from about 6 to 7. And what this means? It means in plain and simple English that maximum ground motion may be observed not necessarily at the closest distance to the fault, but at certain distance. I will come to the speculations how we explain this, but let's start with real data. As far as I know, there are 4 well-recorded in the near-field earthquakes in California: Parkfield, Imperial Valley, Northridge, and Loma Prieta. Now, if you really look at how well they are recorded, I would say that only 2 of them, Parkfield and Imperial Valley, are really well recorded in the near field. At the full distance of less than 5 kilometers, there are only there are 0 stations for Northridge, and there are only 2 stations for Loma Prieta. And for distances of up to 10 kilometers, again, same picture, very many records from Parkfield, relatively many from Imperial Valley, and much less for Northridge and Loma Prieta. Now, let's look at these first 2. Do they have a bump at certain distance? I would say yes. We are saying yes. Now, of course, it can be a matter of interpretation, but clearly there are some increase in amplitudes at certain distance, and this bump is actually magnitude dependent. Basically, the bigger is magnitude, the farther is this corner period, which is another difference in our model. Basically, our model we try to be as physical as possible. This is why this flat area, at least, is proportional to magnitude. And the larger is the magnitude, the farther is this corner distance or slope. Now, these are two well-recorded earthquakes, Imperial Valley and Parkfield. Now, let's go to the two others, which are not as well recorded, but also more or less okay recorded. I would not say that they confirm the bump, but they definitely don't eliminate the idea of bump. Now, that's a summary. How many out of these 4 well-recorded earthquakes demonstrate bump? 2 out of 4. That's our opinion. How many are not conclusive? Another 2. Now, I've been asked many times about how we explain this bump. And here come, in a way, certain speculations. First, recently we found similar results in publication in BSSA. Oh, sorry. It is Chapman and Goodby, BSSA 2012. They also demonstrated bump or amplification of ground motion at certain distance from the fault, not exactly on the fault. And their explanation, it's a quote from them. I don't have to do anything with this. This is because of wave propagation through a one-dimensional layered Earth model. That comes from Martin Chapman. Now, in real life, in their case, these are ground motion simulations, similar to what we saw yesterday. But in real life, I would speculate that, of course, this is the first effect that they presented. It can be also directivity. It can be also partially nonlinear behavior of media in the near source area. And another very important factor is our common way of measuring distance. We are measuring distance closest to the fault. I don't recall who earlier suggested, maybe it was you, Ken, but it doesn't matter. Somebody suggested to use not the closest distance to the fault, but distance to the biggest or most important asperity. I would suspect that if we will start measuring distance from the strongest asperity or strongest part of the fault, the bump may go away. Basically, I think it's a combination of all these effects. That's my answer to the probably main question that I have many times from audience. Now, style of faulting. Honestly, we did very simple work. We used basically same as publication of Sadi et al. 97, where they took factor as 1 for strike slip, 28% higher for dip slips, and we used F114, basically half and half for mixed events. Now, for normal faulting, we didn't have any constraints, because this is why we just stayed with same number 1. We treat normal faults as same as strike slips. Now, in support of this, we actually looked at the data, and we didn't see any really problems with this more or less simple interpretation. Now, ZTOR. Okay. I have to go back and probably read the last phrase. Our modeling philosophy is to avoid any independent parameters, the thing that Ralph was mentioning, which are not present in the catalogs, which cannot be easily determined by shake maps or engineers who work with those models. And okay, now my experience, when I looked at this information, I really find that it is very difficult to constrain ZTOR, from my experience. From this point of view, I would say that I like the idea of depths to hypercenter depths. Thank you. Just had some blockage in my mind. Thank you. Hypercenter depths. But okay, to make it plain and simple, no, we didn't use it. But okay, the important factor, in a way, there is a correlation between deep sleeps or reverse faults and ZTOR. Basically, from my experience, almost all reverse faults are relatively deep relative to strike slips. And this is why kind of this factor of 1.28 for reverse fault relative to 1.0 is partially taking care of the depth to the rupture, to the surface to the rupture. Now, hanging wall effect. I'm sorry, and I have to say this, we were not allowed to participate in NGA-West 2, and we were not given access to NGA-West database and information at the time when it was developed. I specifically asked a few times, and I was told no other participants except whatever was decided before. This is why kind of, I don't know what is the latest finding, but previously I tested I tested all models, and I can remind you that I was an official reviewer from CGS when I worked in California. And I have to say that Abrahamson and Silva model and Chu and Young model with their hanging wall effect of 2008 produced sometimes unreliable results. I specifically, what I mean unreliable, I took all these models and I put different solutions, fault plane solutions published by seismologists. And I have it in my paper. And there are 5 different solutions. And depending upon which solution you put, you can have variation of PGA for U2 models 2008 from 0.2 G to 0.6 G in the near field. Now, don't want to judge anybody, but from my experience, previous experience, I was not really satisfied with hanging wall effect. And I can only say when I will see testing of the new hanging wall effect, we will be happy to try it because in our filter-based approach, it's pretty simple. We just multiply by another filter. As soon as community will agree on this hanging wall effect, we will be happy to implement it. Of course, in this case, we will need to rerun everything because it may affect residuals and everything else. Okay, constraint for magnitude 7, 8. These are earthquakes which helped us to constrain between magnitude 7 and 8. And of course, Denali is not as good as Chichi, but basically these are earthquakes that we use to constrain our magnitude scaling. It may be far from perfect at magnitude close to 8.
I think our question here is, did you apply any other constraint on how it's scaled other than an empirical, fitting these earthquakes? Did you say it must increase with magnitude, it must do something like that?
Oh, okay. Yes, yes. We actually agreed, or we stayed with the idea that we heard at previous NJ models that there is a magnitude saturation. And basically, I just made a comparison to the plot that Yusuf was showing, how our model behaved at 30 kilometers from the fault. And it's pretty similar to what you guys are having. It's a little bit lower at magnitude 8, but it's very close at 5, 6, and start deviating slightly lower at magnitude 8. That's how it really works. Did I answer?
Yeah.
Okay, sure. Now, at this point, I will pass the microphone probably to Errol. We were strongly criticized by our use of standard deviation. Basically, in our model, it's very simple. It is simply period dependent, and there is no difference. We didn't differentiate between different inter and intra-event residuals, but listening to this criticism, Errol did a lot of work, and can you please come here?
But
So the discussion is after error?
yeah, but let's
Now we have Sinan.
yeah, but let's do a little bit
Discussion of the whole thing.
now about
After.
before you sit down. Let's cover some of the topics that you just
Yes,
that's,
sure.
That's what you want. Right?
Okay, okay.
So can we go back a couple on, you've got two issues of, let's even go to hanging wall. So
Yes.
you're using R rupture as your distance metric.
Correct.
So you say hanging wall effect isn't considered in the BSSA model. That's because they use the join your board distance metric, which
Okay.
already has it, right? It's very similar to the hanging wall effects that are put into the rupture, the R rupture models. So I think you do want to look at or get your residuals plotted over the hanging wall, with those sites and see what the results are. Because the numerical simulations are pretty robust in saying there's a big difference between the footwall and the hanging wall.
Oh, okay. Please understand me correctly. In no way I'm saying there is no difference. I'm saying I didn't see yet the model which kind of well discussed and well tested. That's what I'm saying. It doesn't mean it doesn't exist.
Yeah,
I'm saying I didn't see at the time.
The 08 models, this was one of our biggest uncertainties, is trying to produce the hanging wall effects. Because I agree they were very large differences.
Yes.
But that told us we didn't know very well or didn't have a good constraint on what was happening.
Okay, please understand me correctly. In no way I want to criticize anybody. The whole purpose of this was to say that at the moment of creating this model, we didn't see anything which satisfied our criteria of robustness.
You can criticize us, that's fine.
That's fine.
Okay.
I can. But the purpose of this was that
Sure.
simply at the time of creation of the model, there was no such model available, or at least known to us.
Yusuf, you had a question?
Third bullet, you know
Yes.
that the database is public since May. You can download it, whatever we use to develop GMPs, right? So there's nothing secret about these things. In fact, I really, truly believe on the face of the earth, if there is only one open database is this, because we are not hiding anything. So you have the database.
Okay, let me.
I have a question.
Okay, Errol, I'll answer this question. I specifically asked you in November, and this question was asked to you, and you told me that the database is not available and data are not available.
Did I give you a reason?
Yes.
What was
the
it?
reason was that it is not well constrained. I'm not. Yusuf, please let's stay away from. I'm explaining why NJ West 2 basically didn't come through our attention, because at the time of creation of this model, it was not available to us. It was made available on May 15th, if I'm right, and it was much later than all testing was done. Now we are planning to look at this, but you understand that looking at this means that we have to rerun everything. That's why basically if we will start rerunning everything now, I'm explaining. I'm not attacking you. Please understand.
Vladimir, I'm sorry. May I ask you a favor? We're running very late,
fine.
and I
Please,
would like to re-steer the discussions towards the goal of our workshop. So it's very critical for us to be able to capture the perspectives of the speakers that are invited to these sessions. So if we can move forward, please,
Sure.
with the technical discussions, that would be greatly appreciated. And then on a separate base, you can keep talking about the issues that you raised. I'm sorry for stepping in.
I'm going to wrap up very quickly. Actually, what we did is through the whole regression, we did multi-stage regression using nonlinear optimization and come up with the total, total sigma and total residuals. And then after we used mixed effect analysis, basically maximum likelihood, mixed effect approach. The post-predict was, kindly provided all his codes, so we generated all the intra and inter-event residuals. And then after we beamed them, and then in the next slides, we're going to show us, all the beans values, their standard, the deviations, as well as our, the trend lines. And we checked the periods, starting from PGA. So I'm going to show all the, representative results next in the slides. So our model basically showed no bias against the event terms, as well as any independent estimation parameters, magnitude, distance, VS30 and C1.5 that we used. Okay. So these are the intra-event residual terms. So in in each plot, so basically we are showing the means. The black lines are the mean values, and the standard deviations are shown by the red vertical lines. So the total residuals here, PGA, and against the distance, as well as on the right side for the VS30. So the bottom plot is the intra-event residuals. It's difficult to see, but we have this, the trend line going, it's a dash red line. So we fit linear square fit. So basically the slope of our trend line is, practically zero. So we don't show any bias in terms of distance as well as the VS30. So this is our whole database. It's about 2,500 data points. So this is for the Z1.5. Again, our model is, fitting very well to the data. So our, the slope for the intra-event residual is almost zero. So when we look at the event terms, inter-event residuals, so we have about, the 40 earthquakes here. So we have the PGA, SA at 0.2 second, as well as the spectral acceleration at 1 second. Again, the red dashed line shows the, our trend. Again, the slope is, is very close to zero. Practically, we don't have any bias in any of these event terms as well as the intra-event terms. So we're about to finish our OpenFire report. So we're going to provide all these, the figures and as well as the other periods. So this information is going to be available, like publicly soon. So in summary, just to wrap up our presentation that Vladimir started, so our ground motion prediction equation can be adjusted to other regions. We have now included Q factor to compensate that. So our model is not multi-pages long equations. They are very simple. Our spectral acceleration is a function of spectral period, so it's a smooth function. So we didn't do any smoothing on any of our coefficients. So it has very minimum number of coefficients as well as the independent parameters to be used. And so we did the residual analysis to come up with all the inter-event terms, and then we used the mixed effect approach, show that our model is unbiased. So that's the top of my presentation.
So is it possible for us then to get the intra-event or
Sure.
your estimates of tau and phi then from those residuals?
Yeah, we can provide.
Okay, great, thanks. Sorry.
Oh, yeah.
Doug Drager. Yesterday we saw some examples looking at the hanging wall. And my recollection was that the curves from your method had a broader plateau. And so what I was wondering is if that is something that just, it comes about from this distance-dependent bump that you have. I didn't catch whether it was symmetric or not. It probably was.
That's okay. It should be on. It is possible it's coming from the bump, because the bump is distance dependent and magnitude dependent. Basically, the bump, the larger is the magnitude, the lower is corner frequency. The longer is the period. Basically, I'm misspeaking. Basically, the larger is the magnitude, the bigger is the area in which there is no attenuation. Basically, the flat period. That's the point. This is why probably you see this effect in our model.
Right?
That's part of what our hanging wall model does, is it flattens it out over the beginning part. So some of those things might trade off in there as well.
That's possible because again, our experience, for example, depth to the your Z-Tor is in a way related to
Style of faulting. Yeah, no, I completely agree with that. We have no style of faulting factor for reverse anymore because it's accommodated by the depth term, and those things trade off completely.
Exactly, and I don't recall exactly which model I looked at the previous models. You're right, it is much less difference. Yes, it's a trade-off. But again, our logic was to make this model usable by engineers. They don't have to search or look for help from seismologists. Let's put it this way.
Okay, let's move on.
Thank you.
I think Sinan is next, right?